Hi, my name is Onur Danacı. Today I'll be talking about multi-spatial mode intensity difference squeezing and numerical calibration for hot atomic vapor four-way mixing systems. So currently I'm affiliated with IBM HBCU Quantum Center at Harvard University, DC. But like this work is based upon my research with my PhD supervisor, Ryan Glasser, on our unpublished work funded by US Naval Research Laboratory. So this is my dissertation work. So what is our motivation? So like our main motivation is the our previous experiments in this hot atomic vapor nonlinear optical systems. So we saw, so our workhorse is a hot atomic vapor medium, a Chi-3 medium, which is mostly like, for example, maybe filled with rubidium atoms that are heated up until 110 degrees Celsius. And we pump the system with a spatial structured classical and strong pump beam. And we also seed this with some slight inclination with a seeding probe beam, such that they are somehow overlap within the systems, and this overlap profile is like amplified. So we create some sort of like generated probe beam on in addition to the seeding probe beam and the generated conjugate beam. For example, in one of our experiments in 2005, is we used this spatially non-Gaussian and spatially large pump beam, this donut-shaped beam, which is actually a Bessel-Gauss beam. And we found that once it is overlapped with a spatially smaller seeding probe beam, which is just the center of this, we find that like as soon as the four-way mixing is turned on, we create this bullseye pattern for both the generated probe beam and generated conjugate beam. We find this like these bullseye patterns are basically mimicking each other. We are creating twin beams. And second, we find that like once we take the 2D Fourier transforms, like through passing them through a thin lens, we find that like it has some sort of like analysis profile, meaning that like they see through this nonlinear gain medium, they experience some sort of a gain medium 3D aperturing. And the previous theory does not account for this, for previous semi-classical and previous full quantum mechanics. So that's why like, we first try to develop this. So to develop this, like we use paraxial optical beams coming in like the context of Fresnel diffraction or optical Schrödinger equation. So these are we have Laguerre Gauss solutions once we solve this in cylindrical coordinates, and these solutions are complete orthonormal set of basis functions. So not only beams, but you can also expand any sort of like image by using this set. But these sets are kind of like coherent states in quantum optics. They are overcomplete, meaning that like we need to be setting its basis set through focal position and waist parameter. Otherwise, like they are not orthonormal anymore. So we need to be make sure that like we are using the right set. And also like we can obtain the set naturally without any a prior scale information from the m² parameter of the beam itself in your experiments. And you can use this for your Fresnel diffraction calculations or like the homogeneous domain calculations just by, for example, you have a beam, you decompose this into Laguerre Gauss modes at any plane z calc throughout your propagation axis, and once you find your mode coefficients for any given set, you can propagate this forward or backwards. And this is actually corresponding to propagator of homogeneous paraxial wave equation. So this 2D decomposition and using this to propagate is actually corresponding to the propagator. How about the non-homogeneous paraxial wave equation that we encounter for this nonlinear optical systems once we have like some sort of source term? In this case, we can make some approximations based upon our experimental results. As I told again, like we see gain media aperturing, meaning that our pump and seeding probe beams propagate through this nonlinear media as if it's a homogeneous domain, but their overlap profile throughout this nonlinear medium leads to this creation of like the generated probe and conjugate beam. Also, in this experiment, we see that like phase matching can be ignored up to the very end. Meaning that actually we can use firstborn approximation to model this kind of system, this overlap profile to calculate what kind of beams are amplified. And this actually corresponds to getting some sort of 3D, unlike the 2D, the 3D overlap integrals, 3D mod, LG mode decomposition, and this corresponds to the Green's function of of paraxial wave equation. So this is something like this. Let's say you have your classical pump beam pumping the system, and then like depending on its spatial shape, and also the spatial shape of your seeding probe beam. Let's say it is like your seeding probe beam is in like the Laguerre Gauss mode L and P indices. Then your overlap integral for two-mode squeezing is actually structured by this. Only in this case, like the L and P modes of the probe are coupling to L prime P prime modes. Depending on the pump. So this vacuum seeding cannot be amplifying all the modes, but the modes that are basically constrained by the spatial mode structure of pump and probe. And again, like you create this generated probe and generated conjugate modes, and then like there is some sort of quantum correlations between them, the two mode squeezing between them. And so we use this techniques, this theory to interpret like the intense difference squeezing experiments. And usually before, like the naive interpretation of intense difference squeezing was just the parametric amplification. Let's say you have 0-0 mode, like Gaussian pump beam, and then like you have like some sort of Gaussian probe beam. Then you create a Gaussian probe and conjugate, and they are like, let's see, this bright seeding beam has like the is a coherent state alpha, and you are amplifying your probe and conjugate beams through gain, and at the end, actually, like naive interpretation is that like the difference, electronic difference, is related to the gain, and you can calculate gain from that. But this assumes that if you take your pump beam large enough, that you can take this as a plane wave, because its beam waist is large, its Rayleigh range is huge, and it's like basically more or less some sort of constant gamma all throughout this. Its amplitude is gamma all throughout this, but actually it's not true. Like this is true if and only if this ratio goes to infinity. And in realistically, actually, we need to taking account of like what sort of Laguerre-Gauss beam set, basis set we are using. And like if we in this case, like even though like you are creating the small Gaussians in this intense difference squeezing experiment, like you see it with a small Gaussian, you have large pump, and you create small Gaussians. Actually, there are more modes in mode. Actually, you are creating these modes, yes, but actually there are many others in mode in this case contributing. And in the realistic case, actually, yes, you have like this parametric amplification between 0-0 modes, like alpha 0-0 and then a conjugate 0-0. But also you have all those contributions coming from vacuum, two-mode squeeze vacuums, like for example 0-1 coupled to 0-0, 0-2 to 0-0, etc. And actually our naive way of like calculating the gain from the intensity difference squeezing is wrong. Actually, there are many precious quantum resources lurking around that we can actually use and access. So we use those experiments to get a fitting parameter for our numerical calibration, and having got that, like, we use this to optimize these quantum experiments by a sort of an algorithm. I call it like control spatially allowed target squeezing by adjacent P. So the main idea is that, like, we choose only one Laguerre Gauss set for pump and seeding beams, and also we choose like the nearest adjacent P mode for the seeding beam, and we structure our pump beam to cancel this effect. What do I mean? For example, like one sort of setup that I propose is that, like, we use, instead of 0-0 seeding pump beam, we use 0-1 seeding probe beam, and we structure our pump beam by using a Fourier hologram in such a way that, like, once it's squared, because two pump beams are annihilated in a four-way mixing experiment, then it cancels the contribution from this, such that, like, this nonlinear polarization profile all throughout this nonlinear medium is a pure Gaussian, and we are creating pure Gaussians in our Laguerre Gauss set. For example, in this case, okay, we have this seeding probe beam in 0-1 mode is parametrically amplified. You parametrically amplify this, and in exchange, you create this 0 for 0-1. You create the 0-0 mode. This is the parametrically amplified. But we also create two more squeeze vacuum. We create the 0-0 probe, and we create this 0-1 conjugate. And this is like vacuum squeezing. And you can filter out this bright modes that would normally obscure you by using the orthonormality of a strong local oscillator beams in homodyne detection. For example, you can use 0-0 local oscillator for the probe and 0-1 local oscillator for the conjugate beam, such that, like, their electronic difference in a spectrum analyzer is giving you the squeezing. I mean, yes, you have parametric amplification between 0 and 0-0, but also you have two more squeezing squeeze vacuum process between 0-0 and 0-1, and you can access them through tailoring your local oscillator. Also, another, let's say you want to create two modes. Let's say you want to create a superposition of 0-0 and 0-1 beams. Again, like, you, as a seed, you would use the nearest adjacent P mode, 0-2 mode, and you tailor your structure, your pump beam in such a way to cancel this, like this double analysis beam, such that, like, their overlap throughout the nonlinear medium is a superposition of these beams, and you create this beam. Yes, again, you have like this parametric amplification of the 0-2 beam in exchange for this in the conjugate beam, but also you are creating 0-0 and 0-1 over here. Like, you create this beam, and you can filter out and access only this by this structured local oscillator for seeding beam, and also you can access to its counterpart in the conjugate beam by structuring your LG-02 local oscillator beam, and in such a way that you can jointly homodyne them. Yes, you have this parametric amplified 0-2s to 0-0, 0-2 to 0-1, but also you have vacuum squeezing for these modes, and you can access this hitherto inaccessible information by carefully tailoring your local oscillator beams and then taking their electronic sum or minus. And again, we found that, like, the naive interpretation of these experiments were for quantum networking, etc., is not correct. And then, like, we actually extended our calculations to make it more realistic for our experimental results. And we proposed a way to optimize by setting up the Laguerre Gauss mode basis functions and canceling the effects by structuring the pump beam. Thank you so much for listening to me.